Welcome back. Having completed a large module, it is a good time to pause and see where we are going to be going in the next module. Till now, what is that we have done? We have introduced nuclear science and engineering mostly via experiments. It is important to understand the role of measurement technology, what was possible in late 1800s, what kind of um, observations can be obtained from experiments. So this is often the case because of the nature of the problem. Nuclear science and engineering is about uh, how to unravel a many body problem. It's a strongly interacting system which contains many subunits. So experiments are very important, and how do you interpret the observation is also very important. So try to get a feel for how you uh, arrived at major conclusion using the experiments that were done. Then it is always good to start with energetics because even when you are thinking about kinetics or dynamical phenomena, what provides the foundation is the energetics. In macroscopic systems, thermodynamics is very important. Here, in nuclear science and engineering, we cannot really talk in terms of thermodynamics per se, but we can talk about energetics fairly quantitatively. And whenever we are thinking about energetics, energetics is coupled to structure. So one cannot really talk about energetics without having some models for nuclear structure. So you should have a good feel for nuclear structure and energetics by now. And perhaps if there is one plot you have to remember, if there is only one plot you have to remember from this course, that would be the binding energy curve, because uh, energetics foundation is set by this particular feature, right? Uh, this binding energy curve was obtained in a way experimentally, let's say from mass spectroscopy result, but you can only obtain mass from such experiment, but the connection to energy was made via Einstein's theory of relativity, um, uh, from E is equal to mc squared. Without even understanding in detail, just knowing this formula helps you convert the masses obtained and its equivalence to energies. So this is an important feature of energetics. Once you have this, you can start thinking about uh, certain other things, and these thoughts are framed via the two very different nuclear models. In one model, we considered nucleus to be a, like a condensed matter, right? In a way, very condensed matter, um, because the density is quite large. But the other model appeared as a dilute gas. So both had its powers, which seems to suggest that the two different models are applicable in two different regimes and can be utilized for rationalizing perhaps two different features. So we will look into this later in this course, because I've just made a perhaps a vague statement. We'll get back to this, clarifying the statement later in this course as we go to understanding more phenomena. So once this has been done in a typical, let's say, chemical engineering course, what you do is start looking at kinetics. So kinetics is um, how to think through changes at a, let's say, macro level without going into microscopic reasons for change. Those things can be called or referred to as dynamics. But when we talk about kinetics, we are talking about, let's say, phenomenological model for documenting rates of change. And while we do so, we will appeal to certain mechanisms, but first we need to document how things change in nuclear uh, systems and nuclear reactions. That will be taken up in the, uh, this is going to be a lengthy module wherein we will look at the kinetics of alpha decay, beta decay, and certain models for rationalizing the changes that are observed. So that will be the next module, which will again have many lectures. Thank you.